Hello everyone. Today we're going to talk about the mean and median. The prerequisites for this material are calculus, as in series and integrals, discrete and continuous random variables, and discrete and continuous parametric models. The goals are going to be to define the mean mathematically, to derive the mean of popular models, and then to define the median motivated by a limitation of the mean. Okay, so let's take a look at some motivation for the definition of the mean of a random variable. Imagine that you have data. In this case, the data have discrete values. They are integers, 3, 4, 3, 4, 6, 3. You're probably familiar with the concept of averaging. Averaging is a very reasonable way to compute the typical value of a group of numbers. So the idea is that we sum all the numbers and we divide by their number. By the number of values that we actually have. So if we think of these numbers as samples from a random variable, essentially what we're doing is we're weighting each possible value by the fraction of times that it appears in the data set. But as we have many samples, this fraction of samples that are equal to a particular value A, that's exactly the way that we defined, at least intuitively, the probability of A. So if we want to take the average of a random variable, a very reasonable definition is you take each possible value that the random variable can take, you weight it by its probability. We're considering discrete values, so that would be the PMF of the random variable at A in this case, and then you sum it up over all possible values. And again, intuitively, that's essentially averaging the possible values that the random variable can take if we took many samples. We define the mean first moment or expected value of a discrete random variable in exactly this way. Okay, it's this weighted average that is computed by weighting by the PMF. I'm writing here if the sum converges because this sum may not converge in some cases. In those cases, the random variable just does not have a mean. And we'll talk later on about what that actually implies in practice. Okay, so now we're going to compute the mean of some popular parametric models. Let's start with the Bernoulli random variable. If we want to compute the mean, what we have to do is we have to weight each of the possible values of the random variable by the corresponding value of the PMF. In this case, this is very easy. The probability of the Bernoulli being equal to 0 is 1 minus theta. The probability that it's equal to 1 is theta. So the mean is just equal to theta. Let's take a look at the geometric random variable. Exactly the same idea. A geometric random variable can take values from 0 to infinity. Here we're just starting at 1 because at 0 this term that is the possible value times the probability is equal to 0 anyways. So now we have a sum that goes from 1 to infinity and is of this form. Here you have the derivation in the notes. Basically what we're going to do is we're going to apply an identity that comes from the geometric series. And the idea is that you take the identity for the geometric series and you just differentiate on both sides and you get a formula to compute this sum. And the final result is 1 over theta. Again, you have the details about the geometric series in the notes. The interesting thing here is that the expected value or the mean of a geometric random variable is 1 over its parameters. So for example, if we have a fair coin, the mean of times that we're going to have to flip it to get heads is 1 over the probability that the coin is heads. So it's 1 over 1/2, which is equal to 2. Okay, so that gives us a rough idea of how many times we're going to have to flip until we get heads. This is the PMF of a geometric random variable that has theta equals to 0.2. The mean is at 1 over 0.2, which is 5. Now let's take a look at the mean of a Poisson random variable. in order to compute the mean, it's going to be useful to remember the series expansion of the exponential function. Again, we do as usual, we take the possible values of the Poisson and we multiply by the probability. And here we start at 1 because this sum is 0 if k is equal to 0. Sorry, this term is 0 if k is equal to 0. We plug in the PMF of the Poisson. And now what we do is we basically get rid of this k by cancelling it out with the factorial so that we get this term. And now we do a change of variables so that we can express this in terms of the series expansion of the exponential. Okay, after that change of variables, we get this, so that this is basically just equal to lambda times e of lambda by this expression. I strongly recommend that you just try to derive these things on your own. That's not really the focus of the course, okay, like using all these series and so on, but it will be good for you to be at least moderately familiar with them. So I do recommend that at least once or twice you try to derive this on your own. Anyways, then the exponential of minus lambda and the exponential of lambda cancel out, and we get that the Poisson random variable is equal to lambda, which is kind of nice because if you remember, when we derive the PMF of a Poisson random variable, this parameter lambda, I just basically said, it's kind of the what we expect, the number of these events that were happening in an interval that we expect to happen, but I wasn't really giving it a very formal definition. Here we see that it actually corresponds to the mean, which makes a lot of sense from what I just said, right? It's the expected number of these Poisson events that will happen in this interval of interest. When we look at the PMF of a Poisson, in this case, for lambda equals to 25, this is the mean. Okay, it's just equal to 25. So now what happens if we have continuous quantities? Up to now, we have been just talking about discrete random variables. So in that case, let's think again of the intuition. We would get samples from this random variable that are continuous numbers. And even if the real numbers, even if the numbers are real numbers, if we want to get a rough idea of what's a typical value in a group of real numbers, you're still going to compute an average in exactly the same way as you did for the discrete values. So now, what does this mean in terms of the distribution of the continuous random variable? It gets a little bit trickier because now the continuous random variable will have a density instead of a PMF, but we can still do as usual and take limits. So here the idea is that we say, okay, let's take the real line and then let's cut it up in intervals of with epsilon. Okay, I don't know why I drew so many intervals. And now we can think of the average. Oops, sorry about that. I always forget to change this up. Like, we can think of this average as you see how many times you're in here. Okay, let's say that this is A of m. You see how many samples you have there. In particular, you see what fraction of samples fall there, and then you multiply it by that particular value. When this interval, the width of this interval, goes to 0, when it becomes really, really small, that's roughly the same as averaging the samples directly. Okay, but the probability that you land in there is the density times the length of the interval, as if the length of the interval becomes very, very small. When we consider this sum as epsilon goes to 0, so you have like an arbitrarily fine grid, eventually you converge to this integral where you're just weighting each possible value by its density and then afterwards taking the integral. So at the end of the day, a reasonable way of defining the expected value or the mean of a continuous random variable is basically taking the integral of the variable over all its possible values and weighting at each point by the density of the random variable. Okay, that's what we call the mean of a continuous random variable. So now let's again compute the means of some popular parametric models. If we have a uniform random variable that is uniform between theta 1 and theta 2, remember that this PDF is 1 over theta 2 minus theta 1. So we have to integrate over all the values where the density is non-zero, which go from theta 1 to theta 2. And remember that we integrate the variable. So now the antiderivative of a is just a squared over 2. So we have that this integral is equal to theta 2 squared minus theta 1 squared over 2, and then we still have this because of the density. When you cancel up and down, you end up with theta 1 plus theta 2 over 2, which has a very intuitive, result, because when we look at the PDF, it's just the midpoint between theta 1 and theta 2. In this case, theta 1 is equal to 0 and theta 2 is equal to 1. The mean is the midpoint. That's the mean of a uniform random variable. Okay, the midpoint of the interval. Let's take a look at an exponential random variable. Same thing. We have the variable. We plug in the PDF of the exponential. In this case, we integrate by parts, and I'll let you look up the details in the notes. And what happens basically is that here this just goes to 0, and here we recover the integral of the PDF of the exponential from 0 to infinity. This is just equal to 1, and we have this term that is 1 over lambda. So the mean of an exponential random variable is 1 over lambda. And here's a picture showing it. Here is the mean for an exponential random variable with parameter equal to 1. Now let's take a look at the mean of a Gaussian random variable. So if you remember, when we defined the Gaussian random variables, there's a parameter that is actually called the mean, and there's a parameter that is called the variance or standard deviation, depending upon how you define it. Well, we're going to see that very reassuringly, this mean parameter is actually equal to the mean of the random variable. In order to do that, we basically again integrate the variable against the density. Here we're going to do this change of variables so that a is equal to the standard deviation parameter times t plus mu. So now this integral is going to become these two terms. Here we're going to use a trick that we use all over the place. We realize that this is an even function and this is an odd function. So we multiply an odd and an even function, we get an odd function. Okay, so this is an odd function. If you integrate an odd function over a symmetric interval, okay, so just to be clear, we have the origin is here, and what I'm saying is that we're integrating something that is odd. So basically it has the same values on both sides, but this value is exactly minus this value. When you do that, the area here is exactly equal to the area here, but the area here is going to be multiplied by -1. When you integrate an odd function over a symmetric interval around the origin, the result is always 0. Okay, so this is going to be equal to 0, and here we have something that is basically mu times the PDF of the Gaussian from -infinity to infinity, which has to integrate to 1. So our conclusion is that indeed the mean of a Gaussian random variable is equal to its mean parameter, which again is quite reassuring. It makes sense. Okay, so in this case the mean parameter is 0, the mean of the Gaussian random variable is 0. It tells you where the Gaussian random variable is centered, as we had said already intuitively when we defined the Gaussian random variable. And to finish, if you want to estimate the mean from actual data, essentially what you do is you average. But in statistics, we use this fancy word for averaging, which is the sample mean. But again, it's just you take all the values, you sum them up, and you divide by n. That's all the sample mean is. It's just averaging. So now let's take a look at an example. In this data set, there's the salaries of all the NBA players in the 2017-2018 season. The mean is 5.86 million. However, when you look at the distribution, it kind of seems that there's very few players here and a lot of players here, which is a bit weird, right? Because the mean should be a typical value. In fact, there's only 1/3 of the players that are here, and there's 2/3 of players here. Okay, actually less than 2/3 here, less than 1/3 here, and more than 2/3 there, to the left of the mean. The reason this happens is that the mean can be severely distorted by outliers or extreme values, and here we have some players, so the players are these black lines here, that have extremely high salaries. So think LeBron James and people like this. And because of that, the mean gets distorted and is larger than you would think if you look at the bulk of the population. To illustrate this, let's take a look at an example where we have a distribution that is mostly around 0 but has some extreme values. In this case around 100, but in general, let's say that the extreme values are between x minus 0.5 and x plus 0.5. And the density is uniform. Okay, so there's the same density here as here, but the bulk of the population is here. So let's compute the mean of this random variable. When we compute the mean, we integrate from minus 45 to minus 4.5 to 4.5. So we integrate over this, and then we have to integrate over the extreme values that go from x minus 0.5 to x plus 0.5. This integral, because this guy is uniform between minus 4.5 and 4.5, this happens to be an odd function, okay, because a is odd. So this integral is actually going to be equal to 0 by the argument that we said before. So we only have to worry about the second term. When we integrate the second term, the antiderivative of a is a squared over 2. So basically we get x plus 0.5 squared minus x minus 0.5 squared. When we expand this, okay, I can do this quickly. You have x squared plus x plus 1 minus x squared. And then here we have minus x, but it becomes plus x minus 1. Okay, so this is just going to be equal to 2x, and the 2 is going to cancel with the 2 here. So basically, what we get is x divided by 10. The thing is that now the mean completely depends on x. It's linear in x. So imagine that x is equal to 1,000,000, then the mean is equal to 1,000,000, even though most values are around 0. Okay, so this would say, oh, a typical value is 1,000,000 just because we have taken this part and made it really, really, really large. So the mean is going to be completely driven by extreme values if there's a small fraction of the values that is indeed extreme. So in those cases, the mean is going to be completely distorted by the very large values, okay, as shown by this example. However, let's take a look at an alternative. Okay, yeah, so here, for example, if we set x equal to 100, then the mean is here, completely outside the this interval where most of the values are. Just because, again, there's these extreme values that are pulling the mean in that way. So what I was saying is, let's now take a look at an alternative to the mean, which is called the median. For a discrete random variable, the median the definition of the median is a little bit weird. So let's take a look at the definition of a continuous, the median for the continuous random variable. For a continuous random variable, the median is the number m such that if you integrate it until m, you get half of the probability. Okay, so basically the probability that a is smaller or equal to m is exactly 1/2. This is also what happens here, except that in the case of discrete random variables, you can have very weird situations where maybe the random variable is equal to 1/3 here and 2/3 here. So then in that case, it's a bit tricky to define the mean. Okay? Does that make sense? So in this case, the mean would actually be here according to the definition, but for discrete random variables, it gets a little bit weird. You have to think essentially of the definition of the mean as the mean is the value such that the probability that the random variable is to the left or to the right is 1/2. Okay, that's the way to think about it. And again, there might be some weird exceptions in the case of discrete random variables, and that's why we have this more general definition here. Okay, but the idea is the median is the midpoint of the PDF. So let's go take a look at our example. Remember that this random variable had a bulk of the PDF between minus 4.5 and 4.5, and then it had some extreme values between x minus 0.5 and x plus 0.5, and the idea was that when x becomes really, really large, then the mean is going to be distorted and become very large. So what happens with the median? Well, let's take a look at what the CDF up to m is, at least if you remain in the area of the bulk. And in that case, this guy is uniform. Like, remember, by the way, like the PDF is uniform, and that's where this 1/10 comes from. I should have said that, so let me go back and explain. So this is just the value of the PDF. The reason why it's 1/10 is that this interval is length 9, this interval is length 1, so if we have a uniform that is going to integrate to 1, the density has to be 1/10. Okay, I should have said that before. Okay, but let's come back here. This is 1/10 integrated from minus 4.5 to m, so it's just equal to m plus 4.5/10. So if we say that this is equal to 1/2, then m is equal to 5 minus 4.5 equal 0.5. So the cool thing is that the median is just equal to 0.5. It does not depend on x, which makes sense because it's just the midpoint of the PDF. So the midpoint of the PDF is going to stay there no matter where these guys go, okay? Because the piece of the PDF that is here stays the same, and since we're not weighting it when we compute the mean, it doesn't matter that it becomes really, really large. This gives a much more reasonable typical value for this distribution. And in fact, if we apply this idea to the salaries of NBA players, we have that the median is 2.39, and again, by definition, this means that half of the players earn less than 2.4 million, and half of the players earn more. In contrast, for the mean, more than 2/3 of the players earned less, and only a bit less than 1/3 of the players earned more. Okay, so in cases like this, where the distribution contains some very extreme values, if you want to quantify what a typical value is, then the median is usually more reasonable than the mean. Okay, so what have we learned? We have defined the mean mathematically, we have derived the mean of some popular parametric models, and we have pointed out a limitation of the mean, and we have defined the median as an alternative that works better in those cases. Thank you very much.